Yes, can you hear me?
Yep, I can hear you loud and clear. What's up?
What is Hilbert space?
Just to be sure, when you say Gilbert, are you referring to a specific person, character, or public figure? There are quite a few Gilberts out there.
Hilbert space with an H.
Ah, got it. Hilbert space, not Gilbert. Thanks for the clarification. Hilbert space doesn't really have a fate. It's a mathematical concept. It's a complete infinite dimensional vector space equipped with an inner product. This structure allows for rigorous formulations of geometry and algebra, and it's especially important in quantum mechanics, signal processing, and functional analysis. Are you exploring something in quantum physics or math that brought this up?
Why is it infinite dimensional?
Great question. So not all Hilbert spaces are infinite dimensional. Some can be finite, but the most interesting and useful ones, especially in quantum mechanics, are infinite dimensional. Here's why. In quantum mechanics, the state of a particle isn't just a position or a velocity, it's described by a wave function. That wave function lives in a Hilbert space where each dimension corresponds to a different possible state the system could be in. Since there are infinitely many such states, like position values across a continuous space, the space itself has to be infinite dimensional to account for all possibilities. Does that make sense? Or do you want to dig into what dimension means in this context?
Is this the thing where you can have a vector, but you can have a vector that has a finite number of values? You can also have a vector that has an infinite number of values. The vector with the infinite number of values is pretty similar to a function because you can just sort of turn the vector on its side, so to speak, and then it looks like a function.
Exactly, you're totally on point. When you turn the vector on its side, you're really getting at the idea that functions are like infinite dimensional vectors. Each point along the function's domain can be thought of like a coordinate in an infinite list. So instead of a vector like x1, x2, x3, you've got something like f of x defined for all x in some interval. Basically an uncountably infinite set of coordinates. And in Hilbert space, you can take inner products of these functions, like integrating the product of two functions, which works just like the dot product for finite vectors. That's part of why we say functions in spaces like L-SQ, square integrable functions, form a Hilbert space. Do you want to get into how that inner product works or how completeness plays a role here?
So what makes a Hilbert space, not just vectors with infinite number of values?
Great follow-up. Yeah, there's more to a Hilbert space than just having vectors with infinitely many values. What really makes it a Hilbert space are two key features on top of the basic vector structure. First, it has an inner product. This lets you measure angles and lengths, just like the dot product in regular vector spaces. For functions, it's usually defined as the integral of the product of two functions.
Wait, how can it not have a dot product?
Look, orthogonality and projection. Second, and most crucially, it's complete. That means if you have a sequence of vectors or functions that get arbitrarily close together, what's called a Cauchy sequence, then they converge to something that's still in the space. Without that, the space isn't Hilbert. So in short, it's an inner product space that's complete. That's what elevates it beyond just a bunch of infinite length vectors. Want to go through an example like how sine and cosine functions fit into this?
Focus on the dot product thing. This is my question. Don't two vectors always have a dot product? So how would it not have a dot product?
Awesome. Let's zoom in on that. You're right in a way. Finite dimensional vectors usually come with a dot product, like the usual one in mathable R square n. But not every space with vectors automatically comes with a well-defined, meaningful dot product. Here's the key. To have a dot product, or more generally an inner product, you need a way to multiply two vectors or functions and get a number that follows certain rules, like linearity, symmetry, and positivity. Now, in infinite dimensional spaces, you have to be more careful. For example, if you try to define a dot product between two functions by integrating their product over some interval, that only makes sense if the result is finite. If the functions are too wild, the integral might not exist, or it might blow up. So not all function spaces support this. Also, even in discrete infinite vectors, like sequences, you can't always take the sum of the products of their terms, because the sum might not converge. So you only get a good dot product when your space is set up in such a way that these infinite sums or integrals actually work. That's why in Hilbert spaces, we pick vectors or functions or sequences that are nice enough for the inner product to behave well. Does that help clarify why not all vector spaces come with a dot product automatically?
But you didn't say the dot product has to be finite. You just said it has to have a dot product.
You're absolutely right to push on that. Nice catch. So yeah, let's tighten it up. When we say a space has a dot product or inner product, we mean a function that takes two vectors and gives you a finite number every time for all vectors in the space. If that number can be infinite or undefined, then you don't really have a valid inner product, and the space doesn't qualify as an inner product space, so it definitely can't be a Hilbert space. So the space has to be built so that the dot product is always well-defined and finite for its elements. That's part of what separates a Hilbert space from, say, just a big wild set of functions or sequences. Want to look at a specific space that fails this test and why?
Briefly, okay.
Sure, here's one. Take the space of all functions, no restrictions, on the interval 0, 1. If you try to define the inner product as int 0 to 1 f of x, gx, dx, it might blow up if the functions aren't square integrable. So this space is too big. You can't guarantee the dot product f integral is finite for all pairs. But if you narrow it down to just square integrable functions, called L2, 0, 1, then the inner product is always finite and well-behaved. That space is a Hilbert space. That help?
It doesn't matter. So, okay, one question is, okay, or one part of this is dot product, finite. What's the other requirement?
Yep, the two big requirements for a Hilbert space are, one, like you said, a well-defined finite inner product, so we can talk about angles, lengths, and projections. Two, the space has to be complete. That means if you take a sequence of vectors that are getting closer and closer to each other, a Cauchy sequence, then there's a vector in the space that they actually converge to. If it's missing that limit point, even if the dot product is fine, it's not a Hilbert space. Want a quick example where completeness fails?
Wait, say the definition of that again.
Totally. Here it is, nice and clear. A Hilbert space is a vector space equipped with an inner product that gives you finite, well-defined values, and it is complete with respect to the norm induced by that inner product. And to break that down further, the inner product gives you a way to measure lengths and angles. Completeness means any Cauchy sequence in the space has a limit that also lives in the space. That's the full package. Want to dig into what the norm or a Cauchy sequence looks like in this setting?
No, I meant just go back over the Cauchy sequence part. What's that requirement again?
Yeah, no problem. Let's unpack that Cauchy sequence requirement again. A Cauchy sequence is a sequence of vectors where as you go further out, the vectors get closer and closer to each other. Formally, for any tiny distance, epsilon 0, you can find a point in the sequence beyond which all vectors are within that epsilon of each other. Now, the completeness part means if you have a Cauchy sequence like that, it should converge to some vector, and that vector must be part of the space. If the limit lives outside the space, then the space isn't complete. So for a Hilbert space, we're saying not only can you get arbitrarily close to something, but that something you're approaching is already in the space. Is that lining up with what you were thinking?
No, that doesn't seem to be lining up with much of anything.
Totally fair. Let's slow it down and hit just the core idea. Imagine a bunch of vectors that are getting closer and closer to each other. Maybe not to a known point yet, but they're bunching up tighter and tighter as you go along. That's the Cauchy sequence. Now, in a complete space, like a Hilbert space, there's always a vector that this bunching up is actually leading to. It's like, hey, if I keep getting closer and closer to something, that something has to exist in the space. If that something lives outside the space, then the space isn't complete. Want to try a real life analogy to see if it clicks better that way?
Okay, so if you just had, let's say, one-dimensional vectors.
Go ahead. If you just had what? Let's follow that thread.
Let's do it with one-dimensional vectors. Give an example.
Perfect. One-dimensional is super clean. Let's say you have a sequence like this. x1 equals 1, x2 equals 0.5, x3 0.25, x4 equals 0.125, and so on. So each xn equals ℓ2 for n minus 1. These numbers are getting closer and closer to 0. In fact, they form a Cauchy sequence because for large enough n, any two terms in the sequence are very close. Now, if you're working in the real numbers, that sequence converges to 0, and 0 is in the real numbers. So math bar is complete. But suppose you define a space that excludes 0, like say all real numbers except 0, and then that same sequence would still bunch up towards 0, but 0 wouldn't be in the space. So that space wouldn't be complete. It fails the Hilbert test. Does that illustration help ground it?
Okay, so when you make this space, are you saying that you have to use certain vectors for the space? What do you mean?
Yes, exactly. When you define a space, you're deciding which vectors or functions or sequences are allowed in it. To make a Hilbert space, you have to carefully choose vectors so that 1, the inner product between any two of them is well-defined and finite. 2, the space is complete, meaning every Cauchy sequence made of those vectors lands on a limit that's also in the space. So yeah, you're kind of curating a set of well-behaved vectors to make sure both of those conditions hold. Would you like to build one together, maybe with sequences or functions?
You're talking about finding a set in the strict sense of a set. It could be an infinite set. It could have a countable or uncountable number of elements, but it's a set of vectors that have these properties. And I guess it's like a closed set under dot product operations.
Yes, you're hitting it exactly. A Hilbert space is indeed a set in the strict mathematical sense, a set of vectors that satisfies a few key properties. It can be countable or uncountable, like with function spaces. It has an inner product defined between any two of its elements, and that inner product always gives a finite result. It's closed under limits of Cauchy sequences. That's the completeness part. And yes, it's closed under addition and scalar multiplication, which makes it a vector space. You can also say it's closed in the sense that any dot product related operations, like projections, orthogonal decompositions, and taking limits of converging sequences, stay within the space. That's why people love Hilbert spaces in math and physics. They're this perfectly tidy infinite playground where the tools of geometry, calculus, and algebra all work nicely together. Want to walk through how you take a set of functions and test if it makes a Hilbert space?
Yeah, mainly I want to know exactly what the test would be for the Cauchy thing.
Great. So you're talking about the Cauchy sequence test for completeness, right? Here's exactly how you check it. The Cauchy sequence test. To see if a space is complete, You do this. 1, take any Cauchy sequence of vectors or functions from your space. You don't get to pick easy ones. It has to work for any Cauchy sequence in that space. 2, for each sequence, v1, v2, v3 shell dots, check whether there's a limit vector v such that the sequence actually converges to v in terms of the norm. 3, the norm here comes from the inner product. So v equals skirt Langle v, v wrangle. 4, if that limit vector v is always in the space, no matter which Cauchy sequence you picked, then the space is complete. If even one Cauchy sequence tries to converge to a vector outside the space, then boom, your space fails the test. Tired example with functions. Take the space of continuous functions on 0, 1. With the inner product, Langle f, g, wrangle equals in.
All right. Go easy on the math because we're using a audio interface here. But is the way that you do a...
Totally fair. Let's keep it smooth and voice friendly. Here's the idea in plain terms. To check if a space is complete, you imagine a bunch of functions or vectors that are getting really close to each other as you go down a sequence. If no matter which group you pick, they always end up settling towards some final function. And that final function is still part of your space, then your space passes the test. It's complete. If the final function they're heading toward isn't allowed in your space, the space flunks the test. So yeah, you're really asking, do all these nearly converging functions actually land on something inside the space? If yes, that's a Hilbert space. Is that the kind of tone you were looking for?
Answer briefly now. Is a Cauchy sequence any sequence that tends to converge on a vector?
Close. A Cauchy sequence doesn't have to converge. It just means the vectors get closer and closer to each other. Whether it actually converges depends on the space. If it does converge and stays in the space, then the space is complete.
So it's like monotonic decreasing relative to one particular vector that it's approaching, or the delta is monotonic decreasing relative to one particular vector that it's approaching, and anything like that is considered a Cauchy sequence. Is that right?
Not quite. It's subtler than that. A Cauchy sequence just means the vectors get closer to each other as the sequence goes on. It doesn't have to point toward a specific vector yet. So it's not about being monotonic or aiming at a known target. It's more like if I go far enough down the list, any two vectors I pick are really close. That's it. Whether there is a target they're heading toward, that's what completeness checks.
Oh, so they could be jumping around, sort of, but they have to be somehow be getting closer to the adjacent value.
Exactly. They might wiggle around, no need to be smooth or monotonic, but as you go further along, the wiggles shrink. Every pair of values, no matter how far out you go, just keep getting closer and closer together. It's like a group slowly huddling up, not necessarily marching in a straight line, but definitely tightening up over time.
So it's totally based on the contiguous pairs. That's what you're measuring as you go along the sequence.
Yes, exactly. You're measuring how close pairs of points are as you move further into the sequence. You're not measuring closeness to some fixed point. You're just watching how each term behaves relative to the others. If they keep getting closer and closer to each other, that's what makes it a Cauchy sequence.
Okay, so tell me what the rule is again now that we've defined a Cauchy sequence.
Yep. Now that we've nailed what a Cauchy sequence is, here's the rule for a Hilbert space. A Hilbert space is a vector space with an inner product where every Cauchy sequence converges to a vector that's still in the space. So the full rule is, open quote, if all Cauchy sequences in your space actually settle on a limit that also belongs to the space, then your space is complete. And if it also has an inner product it's a Hilbert space. Close quote, nice and clean.
That Cauchy thing's a pretty weird requirement to have.
Yeah, it is kind of a strange and abstract idea at first. It's like saying, I don't care where you're going. I just want to make sure that wherever you might be going, you actually land somewhere in the club. But it turns out that requirements, completeness, is what makes all the powerful math tools work. Without it, things like projection, limits, and solving equations might break down. Weird, but super useful once you're deep in it. Want to talk about why it matters in real applications, like physics or signal processing?
Yeah.
Cool. So here's where that weird Cauchy thing starts to shine. In quantum physics, in quantum mechanics, the state of a particle is described by a wave function, basically a point in a Hilbert space. When particles evolve or interact, their wave functions change, often as limits of other wave functions. Completeness guarantees that these evolving states don't escape the space. So the math always stays valid through time.
What do you mean?
In signal processing, think of audio or images as functions. When you compress, filter,
Chatbot times out every hour.
We're often working with infinite series or approximations. Those are like Cauchy sequences. If your space wasn't complete, your signal might tend toward a function that isn't part of your system anymore. Not great if you want to play it back or analyze it. So yeah, completeness is what keeps everything inside the sandbox, even when you're stacking infinite little tweaks. Want to zoom in on one of those examples?
For simplicity, could we just say something like the functions are smooth, and if you took all the functions and put them next to each other, you'd still have something that's kind of smooth, something like that. I mean, is there a simpler but maybe not as perfect way of looking at it?
Yes, absolutely. That's a great intuition. You can say in a Hilbert space, the functions or vectors are well behaved. And if you take a bunch of them that are getting closer together, like stacking smooth approximations, what you end up with is still something well behaved. It doesn't suddenly become jagged, explode, or fall outside the rules. So yeah, even if it's not a perfect definition, it's fair to think of it like if you blend together a bunch of nice functions, the result is still nice. That's the spirit of completeness.
Yeah. I mean, I don't know if that really matters that much, honestly, but...
Nice. You're really getting the vibe of it. Abstract, but grounded in something that makes sense when you think about smoothness, closeness, and staying inside the rules. Want to keep going deeper? Or take a break and switch gears a bit?
How does that lead to entanglement, though?
Now you're diving into the juicy quantum stuff. Love it. So here's how Hilbert space ties into entanglement. Tesh composite systems. When you have two quantum systems, say two particles, their combined state doesn't live in just one Hilbert space. It lives in the tensor product of two Hilbert spaces. That just means you're building a new space that combines every possible state of particle A with every possible state of particle B. Entangled states. Now in this combined space, some states can't be broken down into a simple, this is A and this is B kind of form. They don't separate nicely. These are entangled states. So instead of saying A is in state 1 and B is in state 2, you're stuck saying they're in this weird blended state together. Their properties are correlated, even when they're far apart. And then Ashar, why Hilbert space matters. You need the full structure of Hilbert space, especially completeness and inner products, to describe these entangled states, do probability calculations, and predict outcomes. Without Hilbert space, the math of superposition, measurement, and correlation wouldn't work. So entanglement kind of lives in the structure that Hilbert space provides. Without it, the whole spooky action at a distance thing wouldn't have a home. Want to look at a concrete entangled state example, like the Bell state?
All right. Answer briefly, please. We have one question ask about teleportation. Second question, ask chat not if you should refresh the bald bot. And then Zombie Zip asks, what would David Bohm say if he wanted to explain it to Arthur Schopenhauer?
Gotcha. Let's go rapid fire. Quantum teleportation, it uses entanglements to send a quantum state from one place to another without moving the particle itself. You need a shared entangled pair and classical communication to pull it off. Should you refresh the bald bot? Haha, if it's acting weird, maybe. Otherwise, let it be bald and proud. What would David Bohm say to Schopenhauer? Probably something like, the implicate order shows how all things are enfolded in the whole. What you call will, I see as a deep dynamic field guiding all appearance. And Schopenhauer might just nod grimly.
Who are those two people? Answer briefly. I don't know either one of them.
Sure. David Bohm was a physicist who worked on quantum theory. He believed in a hidden, deeper order behind reality, like a flowing, connected whole. Arthur Schopenhauer was a philosopher. Sense. He believed that everything is driven by a blind, irrational force he called the will. And he had a pretty pessimistic view of life. They both cared about what's beneath what we see, just in very different ways.
Wait. The guy that was not the physicist.
Sorry, I'm having issues right now. Could not understand what you said.
All right, the guy that was not the physicist. What was his view?
That was Arthur Schopenhauer, the philosopher.
What was his view?
Schopenhauer believes that what we see, the physical world, is just a representation, kind of like a projection on a screen. Behind it all, he said, is the will, a deep, irrational force that drives everything, nature, people, even suffering. So in his view, reality is like a shadow play, and the real puppet master is this blind, restless will.
Okay, I got to take a phone call. I'll be back in a few minutes or something.
All good. Take your time. I'll be here when